All right, let's dive a little deeper into this coolness. Okay, so in a study to determine whether preferences for self are more or less prevalent than preferences for others, a little tongue-tied there, researchers first asked individuals to identify the person who is most valuable and likable to you or your favorite other. Of the 1,519 individuals surveyed, 42 had chosen themselves as their favorite other. All right, so then that's from this source that you're going from. But here's our data that we want to pull off here. All right, so suppose we randomly select one of the 1,519 individuals surveyed. What's the probability that he or she chose himself or herself as their favorite other? Probability of choosing yourself, that's what it's asking, right? And what does the data say? 42 chose themselves. So this is 42 out of 1,519. Let's get crazy on this because it's kind of a small decimal. 0.02765. Did you get that? Yeah, okay. When I plug that in, that's what I'm getting. All right. Nice. Now, what if two individuals are randomly selected? What's the probability that they both choose themselves as the favorite person? Now, here's the deal. When I'm looking at this, I'm going to scoot it up just a little bit. When I'm looking at this one, this is the probability that first person chose self and the second chose self, right? So this is the probability of the first person chose themselves times the probability, because there's two of them, so we're multiplying, right? That the second chose themselves given that the first person chose themselves. Do you see what's happening here? So it depends on the first one. So this question, how it's being asked, what's a probability that they both chose themselves? So the second person chose themselves given that the first person did also, which means that 42 out of 1519, right? Because that's our first person. But the second person was contingent on the first one, which means that now there are only 1,518 people we're talking about. And if the first person chose, then it only leaves 41. So when you have this conditional here where the first one it makes an impact on that second one, right? It's conditional, then you have to account for that. Nice. Okay, so then plug that into your handy dandy calculator. Yeah, let's go out 5 again. And that's why we did 5, because this one's super small. Yeah. So what'd you get? 0.00074, and then it's 6 after that. So let's round this up to 7.5. 7.5. Okay. Nice. Look at this next part of it, because I want you to see the difference between these two. If compute the probability of randomly selecting two individuals from this group who selected themselves as their favorite, assuming independence. Oh, right? Because independent, we learned that previously, and so we're amazing. Independent means one is not dependent upon the other. On this first section, we have two people, but they're dependent on the other. Here, we're saying they're not. Two completely independent scenarios. So how do we set up that probability? If we're doing the first and the second, yeah, you just straight up go with it. So 42 out of 1519, and then the second one has nothing to do with it. It's its own scenario. So it's 42 out of 1519. So you have the exact same. It's two independent events. It's two completely independent events. All right. Okay. So you're not doing them consecutive order. That's not what's happening here. Whenever it says independence, then one's not dependent on the other one, and then that makes that impact there. All right. So we have 0.000076. Nearly the same, right? Yeah. Nearly the same. So that's awesome. Okay. Let's look at this last concept that we're going to throw down right here. The concept that your sample is less than 5% of your population. All right? Your sample is less than 5% of your population. If a small random samples are taken from a large population without replacement, right? So we're hanging on to them. It is reasonable to assume independence of events. So if small samples are taken from a large population without replacement, it's reasonable to assume independence of events. As a rule of thumb, if the sample size is less than 5%, we treat the events as independent. So I don't have to go through all of that mess. Two events, E and F, are independent if the probability of E given F is equal to the probability of E, or equivalently, if the probability of F given E is equal to the probability of F. So either one, right? Whether I am looking at the probability here of just the numerator or the probability here, just the numerator. Either way, whenever I have two things that are related, if that works out, then we can just think about them as reasonable. Now, I want you to notice parts B and C right here. So based on this new little rule that we just pulled out, look at what's happening. Up here, we said it is given that the second one happens. These are independent. Look how close these values are together. We can use this concept on this parts B and C because these are basically the same. Do you see how that plays out? This is just proof, basically, is what's going on. If a small random samples are taken from large populations without replacement, it's reasonable to assume independence of events. Would this be reasonable to assume independence of events? Yeah. Look how far back this is in the decimal before they even change. Yeah, you can think about this as independent of events. Then you don't have to try to go through and do this part of it and think through it. Whenever you're looking at this concept, which is why this concept is available, we could just multiply them out and that makes it easier. Because frankly, this would be squared, right? And so if I were to say 15 individuals, man, I'm not trying to throw down 15 different things of these. I'm just going to put 15 up here as my exponent if I was talking about that, because I can think about them as being independent. See how that's a benefit to us? Yeah, it's pretty cool, right? Okay, let's do this last example here. Refer to the contingency table, boom, that relates social media use and age. So determine the probability of using social media and the probability of using social media such that you're 35 to 44 years old. Are the events uses social media and 35 to 44 years independent is what we want to look at. Well, I don't know. Let's figure it out. If I look at the probability that uses social media, that is going to be, if I'm looking at this, and it's nice, it already has these totals for it. So uses social media is 338 out of, what's my absolute total? 530. That's handy. If I do that, put that in your calculator, tell me what you get. I get 638. You get that? Okay. And then what about if the probability that you're using social media given that you're 35 to 44 years old? All right. So in this scenario here, your probability, remember this, of social media and, I need to not write a symbol, I need to write the word, and 35 to 44 over just the probability of 35 to 44. Remember, we pulled that off. Okay, so social and 35 to 44, that's 89 out of what's just 35 to 44 as my total. That's 125. So plug that in, and what do you get? 0.712 is what I get. Do we agree with that? We should. Okay. So are these independent? No. So see how close these two were? This is what makes it okay to be independent. Here, when I put this little caveat piece to it, these are not the same. They're not even really close, right? I mean, they're kind of close, but not super close. Not enough to make it okay. So they are not independent. Not independent. Because they're not the same. I'm going to go ahead and write that. Sweet. Well done, guys. Well done. All right. Now, put a wrap on that chapter 5. You guys are doing great. Man, I'm so impressed with you. It's just crazy.